Next, I will show how to apply the one-variance chi-square procedure, but let's discuss its development first. To create the one-mean Z and T procedures and one-proportion Z procedure, we used the central limit theorem for sample means and proportions. While there is no central limit theorem for sample variances, we can still construct a confidence interval using the fact that a certain ratio follows a well-studied chi-squared distribution with n-1 degrees of freedom. So the following probability statement is the equivalent of the generalized empirical rule. It states that we are 1 minus alpha times 100% confident that the ratio is in between the two critical values, chi squared 1 minus alpha over 2 and chi squared alpha over 2. By doing some algebra inside the parentheses, we can conclude that the probability of the sample variance to fall in a specific interval is 1 minus alpha, which can be interpreted in the following way. We are 1 minus alpha times 100% confident that the sample variance as squared is within certain boundaries. Similarly to the previous procedures, but not as obvious, we can flip the population variance and the sample variance in the statement to conclude that we are 1 minus alpha times 100% confident that the population variance is within certain boundaries. Unlike the other procedures, the one-variance chi-square procedure is based on a distribution that is not symmetric. As a result, the confidence interval is not symmetric. While the sample variance as squared is still an unbiased estimate of the population variance, it is not the center of the interval. From the practical point of view, this means that the interval can be found by computing its lower and upper bounds directly with the following formulas. 1 for the lower bound and 1 for the upper bound. Note that we can always turn a confidence interval for the population variance to a confidence interval for the population standard deviation by simply taking the square root of the boundaries. As a result, the following template will be used to construct and interpret the confidence interval for the population variance. For the procedure to work, the following assumptions must be made. The sample must be simple random, and the population must have a normal distribution. Consider the following example. For a certain drug, based on standards set by the agency, a standard deviation of capsule weights of less than 2 milligrams is acceptable. A sample of 10 capsules was taken and the weights are provided below. Construct and interpret a 90% confidence interval for the standard deviation of the weights of all capsules. You may assume that the weights of capsules are normally distributed. First, let's check if all necessary assumptions are satisfied. The sample is simple random. Check. The population has a normal distribution. Check. Also, note that the sample mean and variance are respectively 100.18 and 1.32. Once the assumptions are verified, we may apply the procedure. We will use the following template to construct and interpret the confidence interval. In this problem, the unknown parameter is sigma squared, the weight variance of capsules. The point estimate is the sample variance, which we found to be 1.32. How confident are we that the point estimate 1.32 is equal to exactly the population variance? We are 0% confident of that. The new confidence level that we have set is 90%. So alpha must be set equal to 0.1. Because of the sample size, the degrees of freedom are 9, which is 10 minus 1. Using this information, we compute the critical values, chi-squared 0.95 and chi-squared 0.05. Since the interval is not symmetric, there is no margin of error. Using the formulas, we can compute the lower bound as 1.32 times 9 divided by 16.919, which comes up to 0.70. And we can use the formula to compute the upper bound, which is 1.32 times 9 divided by 3.325, which comes up to 3.57. Now we can interpret the results. We are 90% confident that the weight variance of capsules is between 0.70 and 3.57 milligrams squared. Remember that we can always convert a confidence interval for the population variance to a confidence interval for the population standard deviation by taking square roots of the boundaries. In our example, we are 90% confident that the weight variance of capsules is between 0.70 and 3.57. Therefore, we are 90% confident that the weight standard deviation of capsules is between 0.83 and 1.89 milligrams, well within the standard 2 milligrams. I just showed how to apply the one variance chi-square procedure to construct a confidence interval with a certain level of confidence.